What is the key motivation behind the proposed block transformer architecture?
The key motivation behind the proposed block transformer architecture is to optimize inference throughput by minimizing the wall clock bottlenecks during inference, specifically targeting the costly global self-attention mechanism in vanilla transformers. By employing a global-to-local approach, the block transformer segregates the expensive global modeling to lower layers through block-level decoding, while conducting local modeling within independent blocks at upper layers. This design choice allows for efficient utilization of compute units on inference hardware, significantly reducing KV cache overhead and eliminating the need for pre-filling prompt tokens. The architecture leverages coarse-grained global modeling at the block level to alleviate KV cache bottlenecks, while enabling the token decoder to focus on fine-grained language modeling with minimal impact on throughput. Additionally, the block transformer balances parameter allocation between the global block decoder and the local token decoder, enhancing performance and achieving higher throughput by shortening context lengths in the local module. Overall, the block transformer architecture aims to extend the Pareto frontier of performance to throughput compared to vanilla transformers, showcasing substantial inference time benefits of both global and local modeling in autoregressive transformers.
How does the block transformer model work, and what are the three main components involved in the architecture?
The block transformer model works by employing a global-to-local approach to optimize inference throughput. It separates the comprehension of full context and detailed interactions into two stages. Global context is captured at lower layers in coarse block-level granularity, while local dependencies are resolved at upper layers by decoding multiple subword tokens within each block. The three main components involved in the architecture are 1. Embedder. This component aggregates each block of L_B tokens into an input block embedding. It uses a lookup table to retrieve and concatenate trainable token embeddings, prioritizing simplicity given the small block length in the study. 2. Block decoder. The block decoder contextualizes block representations by attending to preceding blocks. It operates at the block level, producing output block embeddings that enable the token decoder to decode the subsequent block's token contents. This component reduces the context length of a given sequence by L_B compared to a vanilla transformer, thereby improving efficiency. 3. Token decoder. The token decoder locally decodes individual tokens of the next block, using the context block embedding as the sole source of global context information. It eliminates prefill and nearly removes KV cache overhead during batch decoding, allowing for significantly higher compute unit utilization compared to vanilla transformers. The token decoder incorporates the context embedding into the decoding process to effectively leverage the high compute density of the token decoder.
What are the advantages of using a global-to-local approach in the block transformer model compared to traditional transformers?
The advantages of using a global-to-local approach in the block transformer model compared to traditional transformers are significant. Firstly, the global-to-local approach in the block transformer model effectively mitigates the costly bottlenecks associated with global modeling in traditional transformers, such as the KV cache overhead and the need for lengthy prompt tokens during inference. This is achieved by separating global context modeling at lower layers in coarse block-level granularity and resolving local dependencies at upper layers within independent blocks. Secondly, the block transformer model optimizes inference throughput by reducing the KV cache memory requirements, allowing for larger batch sizes and higher compute unit utilization. This results in significantly higher inference efficiency compared to traditional transformers. Additionally, the block transformer model achieves Pareto optimality, demonstrating up to 25 times increase in throughput under prefill-heavy and decode-heavy scenarios. Furthermore, the block transformer model effectively balances training efficiency and inference throughput, showcasing superior perplexity and tripled throughput compared to traditional transformers when considering both training flops and throughput constraints. Lastly, the block transformer model can leverage the initialization from a pre-trained vanilla transformer, enabling efficient training with minimal data and achieving near full performance recovery with just 10% of the original training steps.
How does the block transformer architecture address the bottleneck of KV cache overhead and improve throughput during inference?
The block transformer architecture addresses the bottleneck of KV cache overhead and improves throughput during inference by employing a global-to-local approach. Specifically, the architecture separates the comprehension of full context and detailed interactions into two distinct stages. Global context is captured at lower layers with coarse block-level granularity, while local dependencies are resolved at upper layers by decoding multiple subword tokens within each block. This hierarchical paradigm significantly reduces the KV cache overhead by isolating expensive bottlenecks of global modeling to lower layers and performing local modeling within independent blocks at upper layers. Coarse-grained global modeling at the block level alleviates KV cache bottlenecks by a factor of the block length, while local decoding eliminates the need for prefill and nearly removes KV cache overhead, leading to higher utilization of compute units on inference hardware. The token decoder in the block transformer architecture locally decodes individual tokens of the next block, using the context block embedding as the sole source of global context information, thereby reducing KV cache EO to a linear cost to the full context length. This efficient utilization of context information and compute resources allows for higher throughput and improved memory efficiency compared to vanilla transformer models, ultimately optimizing the trade-off between performance and throughput in language modeling tasks.
What specific results were achieved with the block transformer model in terms of inference throughput and memory efficiency compared to vanilla transformers?
The block transformer model achieved significant results in terms of inference throughput and memory efficiency compared to vanilla transformers. Specifically, the block transformer model demonstrated up to 25 times increase in throughput under prefill-heavy and decode-heavy scenarios, where input and output sequence lengths were 2048 and 128 respectively. This efficiency improvement was attributed to effective reductions in KV cache memory, allowing batch sizes to be about 6 times larger. The model also notably reduced latency in a prefill-heavy setting by caching past KV states of prompts only in the block decoder, without forwarding them to the token decoder. Additionally, the block transformer model showed exponential scaling of throughput as both model size and batch size increased, indicating its potential benefits in practical multi-tenant deployment scenarios. Furthermore, the model's efficient global-to-local modeling approach allowed for higher compute unit utilization compared to vanilla transformers, resulting in significantly higher inference throughput and memory efficiency.
What are the implications of the block transformer model for practical deployment scenarios on cloud platforms and edge devices?
The implications of the block transformer model for practical deployment scenarios on cloud platforms and edge devices are significant. On cloud platforms, the block transformer model offers higher throughput and memory efficiency compared to vanilla transformers. It reduces the KV cache memory overhead, allowing for larger batch sizes and improved compute unit utilization. This results in up to 25 times increase in throughput, especially in prefill-heavy and decode-heavy scenarios. The model can achieve Pareto optimality, balancing performance and throughput efficiently. Additionally, the model can be optimized for multi-tenant deployment scenarios, where aggregating multiple user requests can further enhance throughput. On edge devices, the model's benefits are constrained by memory limitations and small batch sizes. While the model requires more parameters than vanilla transformers, it can still achieve higher speed improvements due to reduced KV cache overhead. However, optimization for on-device scenarios is left for future work. Overall, the block transformer model shows promise for practical deployment on cloud platforms by improving throughput and memory efficiency, while its benefits for edge devices may require further optimization to address memory constraints and small batch sizes.